Hello. Hello. So, hello everyone. So, I hope guys you might have tried the DPP for centrifugal air compressor and you might have solved all the questions. The questions in this DPP were really good. So, let's see whether you have any doubt. In case you have any doubt, then you can see the solutions over here. Okay. So, the first question said centrifugal compressors are used where? So, as we know that there are three types of compressor that we have. One is the reciprocating compressor, second is centrifugal, and third is your axial. So, reciprocating compressors are generally used where you have high pressure ratio required and the volume flow rate is less. In case of axial compressors, you require high pressures and you also have high mass flow. Okay. And in between these two lies your centrifugal air compressors. Centrifugal air compressors are generally used at those locations where you have the pressure ratio developed in a centrifugal air compressor is slightly less. Okay, so you require less pressures, that is in the range of 5 to 7 bars, but the volume flow rate required are high. Okay, so the answer to this question would be option B, that is low pressures and high volume flow rates are required. Guys, if you see high volume flow, centrifugal air compressors, they give you very high volume flow because the velocity with which the air enters inside the compressors are in the range of around 200 meters per second. Okay. So, based on the inlet diameter, that would be around 10 centimeter, 20 centimeter, 25 centimeter or 30 centimeter. You see that a huge amount of air will come inside. Okay. So, that is how you have these centrifugal air compressors. You see that whenever we talk about, let's say, axial compressors, single compressor have multiple stages, 10 to 15. So, per stage, the pressure ratio developed is very less, but combined all 10 stages, you can develop huge pressure ratios, that is in the range of 35 to 40. In case of centrifugal air compressors, you have only one stage. So, there are not multiple stages. If you want to use multiple stages, then you should put the centrifugal compressors in series. So, per compressor, the pressure ratio developed is very less, that is in the range of 5 to 6, and whereas the volume flow rates are high. Understood? So, the option number B will be correct. Moving on to the next question, it says a centrifugal air compressor runs at 15,000 RPM. If the inlet diameter is 15 centimeter and the exit diameter is 30 centimeter, and the inlet temperature is 17 degrees centigrade, then the temperature produced at exit of compressor is, the flow is radial at inlet. So, he has given you that the outlet diameter D outlet, that is your 30 centimeter. He has given inlet diameter is 15 and the flow is radial at the entry to the compressor. Okay. So, that means you see that this is a radial compressor. The centrifugal compressor is a radial compressor. He has not given you what is whether this is backward curved or it is forward curved. If nothing is given, then we will assume that the compressor is always your radial. Okay. So, we will assume this as the radial, and if a radial compressor is there, you can calculate the work required per kg of air will be equal to VW2 multiplied by U2. And we know that this comes out to be equal to U2 square. Okay. So, the work required per kg of airflow is equal to U2 square. And can we calculate U2? So, since he has given you the outlet diameter, that is 30 centimeter, he has also given you N, that is your 30,000 or 15,000 RPM. So, if he has given you N, so U2 can be written as pi D outlet into N divided by 60. Okay. So, you can calculate what is the velocity at the exit, how much this will come out. So, this will come out to be pi multiplied by pi into D. D is 0.3 multiplied by 15,000 divided by 60. So, this is coming out to be 235.61. Okay, 61 meter per second. So, from here you can calculate what is work required per kg of airflow. So, you see that this will come out to be, if I make square of this, this will come out to be 55.516 kilojoule per kg. So, the work that you are adding, the amount of energy that you are adding to the compressor per stage is 55.516. And now we know that work required per stage work compressor divided by mass flow rate of air, that will be equal to what? In case of air compressor, this exactly goes into the enthalpy. So that will be equal to H2 minus H1. Okay, we know that work of compressor is equal to H2 minus H1 multiplied by mass of air. Understanding? So from here you can write this is equal to Cp multiplied by T2 minus T1. So here you can write 55.516, that is equal to 1.005 multiplied by T2 minus T1. Understanding? Okay, so from here I can calculate T2 minus T1, and this T2 minus T1 will be 55.516 divided by 1.005. So that will be very less. So 55.24. Okay, 55.24 degree centigrade. So this is the change in temperature. You can write it as equal to Kelvin, also you can write it as degree centigrade as well. Degree centigrade is equal to Kelvin. Okay, and from here I can calculate T2. So T2 can be calculated as T1 plus 55.24, and T1 is given as 17. So 17 plus 55.24. So I think that should come out to be 72.24 degree centigrade. This was an excellent question, very good question, very conceptually, fundamentally good question. Understood? I hope everybody has understood how to calculate the temperature T2. Okay, so this is your temperature T2 at exit of compressor. So exit of compressor is 72.24 degree centigrade. Is it clear? Moving on to the next question. Next question was again a very good question. It says a centrifugal air compressor having a pressure ratio of 5. So you are given P2 by P1. P2 by P1 is given as 5 and compresses air at a rate of 10 kg per second. So mass flow rate of air is 10 kg per second. Okay. If the initial pressure and temperature are 1 bar and 20 degrees centigrade respectively, then what is the power required to drive the compressor? Take gamma equal to 1.4 and Cp equal to 1.0 kilojoule per kg. So how do we solve this question? Guys, this is not a question of centrifugal compressor. This is a very simple question that you can solve from the concept of your Brayton cycle. So we know that T2 by T1 can be written as P2 by P1 to the power gamma minus 1 over gamma, and this can be written as 5 to the power 0.4 divided by 1.4. What is this value coming? Okay, so this will be 5 to the power 0.4 divided by 1.4. So this is 1.5838. Okay, so 1.5838. So from here you can calculate the temperature T2 that will be at exit of compressor. So that is 475.14. Wait. This is not 300, this is 20 degrees centigrade. Okay, so if it is 20 degrees centigrade, then it will be multiplied by 293. So 1.588 multiplied by 293. So 464. T2 will be equal to 464.06 Kelvin. Okay, so this will be your T2. So if it is T2, now you can calculate what is work required in compressor. Work required in compressor will be equal to mass flow rate of air multiplied by Cp multiplied by T2 minus T1. Okay, and this will come out to be 10 multiplied by 1.005 multiplied by 464.06 minus 293. Is it clear? Okay. So minus of 293 is 171 multiplied by 1.005 multiplied by 10. So this will be 1719. So work required in compressor will be 1719.14 kilojoule per second, or it will be kilowatt. Okay, so this is basically the power, because you are calculating work per second. If you are calculating work per second, then it will be power. Okay, so the power required is 1719. So here the answer given is Oh my God, I have made a small mistake. It is 1.0. I have made a small mistake, so it is 1.0. If it is 1.0 over here, then it is 1.0. Okay, so 1.005, it is 1710. It will come out to be 1710.59. Okay, so see how much difference it has created by the third digit change, 1.005. It has created 9 kilowatt difference over here. Okay, so the answer would be option number C, 1710 kilowatt. Is it clear to everyone? Understood? Okay, so guys, this was again a very easy question. See guys, I have already told you that it is not necessary that you have to always use the Euler's equation of turbo machinery for calculating the power or work done. You can also calculate it by simply using the Brayton cycle or the isentropic compression that we have already seen. Okay, so using steady flow energy equation also you can calculate what is the work required. Understood? Very good. Next question. This was again a fantastic question. This is a centrifugal compressor running at 15,000 RPM. Diameter and whirl velocity at outlet are 500 mm. So diameter D2 is equal to 500 mm. So that is equal to 0.5 meter, and whirl velocity VW2 is equal to 380 meter per second. And he is asking what is the degree of reaction. So he is asking you R. Okay. So we have seen that in case of centrifugal air compressor, we have already studied in the class that in case of centrifugal compressor, R will be equal to 1/2 if blades are radial. If blades are radial, that means VW2 is equal to U2. This we have studied. Okay. But he has given you VW2 over here. So he has given you VW2 is equal to 380 meter per second. And let's calculate U2. What is U2? U2 will be equal to pi into D2N divided by 60. So that will be equal to pi multiplied by 0.5 multiplied by N is, I think, 15,000 RPM. Okay, so 15,000 divided by 60. How much it is coming? I think it should come out to be 392. Okay, so pi multiplied by 0.5 multiplied by 15,000 divided by 60. So 392.7. 392.7 meter per second. And if you see over here, VW2 and U2 both are not same. That means blade might not be radial at the outlet. If the blade are not radial, then degree of reaction is not 50%. So then how do we calculate degree of reaction? So degree of reaction we have calculated as degree of reaction is 1 minus degree of reaction. So guys, I think this expression I have covered in axial compressor. So today we are discussing centrifugal compressor, but this concept I have covered in axial compressor, and there we have derived for centrifugal compressor what is the degree of reaction. So in case if you are seeing this solution before our covering of axial compressor part, then bear with me, because this I am going to teach you in axial compressors. Okay, so degree of reaction is defined as 1 minus V2 square minus V1 square divided by 2 VW2 U2. Okay, so V2 square minus V1 square by 2, this is your kinetic energy change divided by the total power. So degree of reaction is actually defined as VR1 square minus VR2 square divided by 2 divided by VW2 U2. Okay, this is basically the energy conversion. The energy conversion in your compressor divided by the energy, or not only this component, this will also have one more component. So in case of centrifugal compressor, it will be U2 square minus U1 square by 2. So there will be two components. So these two components, in case of centrifugal compressor, you have this energy converted directly into pressure, this energy converted directly into pressure, divided by the total energy supplied. This is what is called as degree of reaction. Okay, degree of reaction is defined as amount of energy that is directly converted into pressure in the blade divided by total amount of energy that you are providing. Okay, so for centrifugal compressor, this comes out to be 50%, 0.5. Okay, understood? So this quantity can also be written as, you see, VW to U2 can be written as V2 square minus V1 square, or if I write it directly over here, it can be written as V2 square minus V1 square by 2 plus U2 square minus U1 square by 2 plus VR1 square minus VR2 square divided by 2. So total energy converted is this. Out of that, the energy that is directly converted into pressure in the blade is this. So this can also be written as 1 minus V2 square minus V1 square divided by the total energy that you are supplying, VW to U2. So in case of centrifugal air compressor, we know that VW1 is equal to 0. So if VW1 is equal to 0, then VW to U2 will be the total power. Okay, and from here I can write 1 minus V2 square minus V1 square. So V2 square is nothing but VW2 square minus VW2 square plus VF2 square, okay, minus V1 square divided by 2 VW2U2, and we know that VF2 and V1 is equal to VF1. V1 is equal to VF1 and we have VF1 is equal to VF2. So from here you can calculate, or you can see that V1 is equal to VF2. So V1 and VF2 both will be same. So degree of reaction in case of centrifugal compressor can also be written as 1 minus VW2 square divided by VW2 multiplied by U2, and you see that this quantity will come out to be 1 minus, so degree of reaction will be equal to 1 minus VW2 divided by U2. Okay, so this is your degree of reaction. So in case of centrifugal compressor, in this question he has already given you. So degree of reaction will be 1 minus VW2 is given as 380 divided by 392.6. Okay, 392.7. Okay, so we will calculate. I think this value will come out to be 2 U2. So you see over here there is a 2 that is remaining. VW2 will cancel. VW2 divided by 2 U2. Okay, so multiplied by 2. So this value will come out to be slightly less than 0.5, that is around 0.48. Okay, and you see that this value come out to be 0.516. So degree of reaction will be equal to 51.6%. That means 51% of the energy that you are supplying to the compressor is directly converted into the pressure inside the blade. Understood? Is it clear to everyone? Okay. So I hope this is clear to everyone. In case you have not been able to solve this question, you would understand this once we discuss the air compressor, axial flow air compressors. Okay, because in that theory I have covered what degree of reaction is. Okay, moving on to the next question. Again, this was a fantastic question. It says a centrifugal air compressor runs at 15,000 RPM. The inlet diameter is 15 centimeter and the exit diameter is 30 centimeter. The slip factor is 0.9 and work input factor is 1.05. So phi S is 0.9 and phi W is 1.05. And he says mass flow rate of air is 5 kg per minute. Okay, and he's asking you what is the power required. So in case of power required, we know that the power required is nothing but m dot A multiplied by phi S phi W multiplied by U2 square. This is how we used to calculate. Okay, so can I calculate MA is given, phi S, phi W is given. Can I calculate U2? Okay, so U2, you can calculate. U2 will be simply written as pi into D2N divided by 60. So that is pi into D is 0.3 multiplied by 15,000 divided by 60. How much is this value coming? How much is this value coming? So this will be pi multiplied by 0.3 multiplied by 15,000 divided by 60. So 235.61. So 235.61. Okay. And you can put this value over here. So power will be equal to m dot, that is 5 divided by 60 multiplied by 0.9 multiplied by 1.05 multiplied by 235.61 whole square. Okay. So I will get 55.516 multiplied by 0.9 multiplied by 1.05 multiplied by 5 divided by 60. So this will come out to be 4.371. So power required is 4.37 kilowatt. Okay. So power required will be 4.37 kilowatt. I hope that is correct. Okay. Let me cross check it with the answer that was provided to you. Okay. So question number, this is question number 4, I think. 5. Question number 5. Yes, 4.37 is what provided to you as well. Understood? So that is correct. Is it clear? Okay. Moving on, let's go to the next question. Next question is again a good question. It says a centrifugal air compressor run at 27,000 RPM. The blade diameter at exit is 20 centimeter and isentropic efficiency of compressor is 90%. If the air enters compressor at 20 degrees centigrade, then the pressure ratio developed in the compressor is. So you see that he is asking you what is the pressure ratio developed. That means P2 by P1. And we know that we can calculate P2 by P1 from what? You see that he has given you isentropic efficiency of the compressor. So if he has given you isentropic efficiency of the compressor, then you have to calculate T2S by T1 to the power gamma over gamma minus 1. So you see that the pressure ratio can be calculated from T2S by T1. Okay. So you have to calculate T2S by T1. How do you calculate T2S by T1? Since he has given you isentropic efficiency, first you have to calculate T2 by T1. Okay. And how do you calculate T2 by T1? To calculate T2 by T1, you have to make use of this RPM and this diameter. So he has given you that the compressor runs at a RPM of 27,000 RPM. So N is 27,000. If N is 27,000 and he has given you diameter D2, diameter D2 is I think 20 centimeter. Okay. So diameter D2 is 0.2 meter. So from N2 and D2, can you calculate U2? Okay. So U2 can be calculated as pi D2N divided by 60. Okay. So pi D2N divided by 60. When we calculate, how much will be the value of this U2? So it will be pi multiplied by 0.2 multiplied by 27,000 divided by 60. That comes out to be 282.74. 282.74 meter per second. Understood? Now this is your velocity U2. Okay. He has not given you anything. He has not given you anything. He says it's a centrifugal air compressor only. So if it's a centrifugal air compressor only, we will assume this has to be radial and the flow to be again radial at inlet. Okay. So from here you can calculate power of the compressor, or you can calculate power by mass flow rate of air. That will be equal to VW2 multiplied by U2, and that will be equal to U2 whole square. Okay. So we can calculate what is U2 whole square. So U2 whole square will be equal to the amount of energy that is added. So 79.943. 79.943 kilojoule per kg. That is amount of power that is actually added per kg. Okay. So if this is the power that is added kilojoule per kg, can you calculate what is the temperature T2? So we know that this power, or P divided by MA, that will be equal to H2 minus H1. That will be equal to Cp T2 minus T1. Okay. So from here I can calculate T2 minus T1. T2 minus T1 will be equal to divided by 1005. So it will be 79.54 Kelvin. 79.54 Kelvin. So this is your T2 minus T1. Okay. He has already given you T1. So the T1 is 22 degrees centigrade. He has given you T1 is 22 degrees centigrade. So if T1 is 22, we can calculate T2. So T2 will be equal to 22 plus 79.54. Okay, so that will be 101. 101.54. 101.54 degrees centigrade, and that will be equal to plus 273, that is 374.54 Kelvin. Why are we converting it into Kelvin? Because we would require T2 by T1. We have to calculate ratio T2 by T1. Okay, so now you see that once you have calculated T2 minus T1, now you can calculate T2s minus T1 divided by T2 minus T1. This is your efficiency of compressor. So from here you can calculate T2s minus T1, that is equal to 0.90. Okay, so efficiency of compressor is given as 90% multiplied by T2s minus T1. So T2s minus T1 is 79.54. Sorry, not T2s minus T1. T2s minus T1 is equal to 0.9 into 79.54. Okay, so this will be 71.59. Okay, and from here you can calculate T2s. So T2s will be 71.59 plus T1 is your 295, 22 degrees centigrade. So this is 366.59. 366.59 Kelvin. So this is what you have got T2s. Now once you have got T2s, you can calculate T2s by T1. Okay, to the power gamma over gamma minus 1. This is your pressure ratio P2 by P1. Okay, so we can calculate this. So 366.59 divided by 295. This is 1.24. 1.24 to the power 1.4 divided by 0.4. So 2.1392. Such a small pressure ratio. I think I have made a mistake somewhere. So 366.59 divided by 295. 1.24. 1.24 to the power 3.5. So 2.1392. Yes, that's correct. Okay. So the pressure ratio developed is P2 by P1, that is 2.14. 2.139 is 2.14. Understood? Okay. So 2.14. Now you see over here, this is a centrifugal air compressor. It is running at 27,000 RPM. Okay. The pressure ratio developed is 2.14. Can you see that this pressure ratio is a very small ratio? So that is the reason why the centrifugal air compressors are what? Which are basically for low pressure and high volume. Is it clear to everyone? Understood? Okay. So this is clear. Let's go to the next question. So guys, these were some of the best questions that you can think of. And now we have the best question, which have a pre-world. So this I told you that I will be telling you this in the DPP solutions. We could not discuss this in the class. Okay, so I will explain it over here. So it says a centrifugal air compressor runs at 20,000 RPM. Air enters at 300 Kelvin and 1 bar. Diameter of inlet of compressor is 10 centimeter and that exit of the blade is 20 centimeter. And there is a pre-wall of 15 degrees centigrade provided at inlet. The work required per kg to run the compressor is. So what happens is, guys, what is pre-whirl? So you see that when we draw the velocity triangle of a centrifugal compressor, this is how a normal, let's say, radial blade is looking like this. Okay, and if you draw the velocity triangle, this is where your relative velocity will be. So this is your VR1. This is let's say I draw it like this. So this is your U1. Okay, and this is your V1. Okay, so this is your U1, this is your V1, which is equal to VF1, and this is your VR1. So you see that this is how a velocity triangle generally looks like in case of a centrifugal air compressor. Now you see that we have already seen that I have told you in the class as well that in case of centrifugal air compressor we have very high axial velocity. So the flow that is coming in, is actually coming in and it is tilted like this. So it is coming axially and it is diverted radially. Okay, it is coming axially and it is made radial. Okay, with help of what? So you have your impeller which is like this. So you see that air comes like this and your impeller is guiding air to upward direction. So this is how is happening. The flow is coming axially and your impeller will divert it in the vertical direction. Okay, so this is how your velocity is coming. So now if you see that you have U1 and you have V1. What is VR1? You see that this is your VR1 and this VR1 is nothing but it will be square root of V1 square plus U1 square. And you see that when you have U1 to be very high and V1 to be very high, generally these centrifugal compressors, they run at very high RPM. When they run at very high RPM, their U1 is very high, their V1 is very high. And because of that, you see that the relative velocity that they might see, it will be very high. It will be somewhere in the range of 500 meter per second. Okay, so recently we have seen that the outlet velocities are 392 meter per second, 300 meter per second. So let's say you have this initial velocity as 300 meter per second. Again, this velocity is 300 meter per second. The velocity that you will be getting over here is root 2 multiplied by 300. That is somewhere around 420 meter per second. Okay, so let's say I write this as 400 meter per second. Now you see that this velocity is more than the supersonic velocity. Okay, this is greater than or sonic velocity. Yes or no? So when this is greater than sonic velocity, you see that when the air is going to enter the blade, what is the velocity that will be seen by the blade? The air that will be coming inside the blade will be more than sonic. The velocity of the air that is coming inside will be more than sonic. And you see that because of that, the flow or the velocity over here is supersonic. If it is supersonic, okay, this velocity is supersonic, you see that there will be a shock wave created over here. This is a shock wave that will be created. And if you have a shock wave that is present at the entry, you will see that when we discuss the compressible flow, we will see that there are huge pressure losses across a shock wave. Okay, so you see that there will be huge losses happening over here. And if there are huge losses happening over here, you see that the power required in your compressor will be very high. Okay, so if the power required is very high, how you can reduce the power required? So the power required, to reduce the power required, what we will do is we want to reduce this relative velocity. So how do you reduce this relative velocity? So this relative velocity can be reduced by guiding your absolute velocity not in this direction, but let's say in this direction. Okay, so what I do is I guide my absolute velocity V1 like this, so that you have this as your V1, this is your U1, this becomes your new VR1. Okay, so this is your VR1 dash. So you see that if your absolute velocity comes like this, not radially, but it comes like this, then your VR1 reduces. So how can you convert this velocity like this? So whatever is the velocity that is coming actually, instead of sending it radially, you have to send it in this direction. So how do we do it, or how do we actually change the motion of the blade, change the motion of this velocity? So what you do is, at the inlet of the impeller or at the inlet of the compressor, you put guide blades, or these are also called as guide vanes. Those guide vanes are tilted like this. So if you see those guide vanes, they are like this. Okay, so guide vanes are provided. So what happens is the flow that is coming like this, the flow that is coming straight like this, first it will be tilted upward. So it will be tilted in the radial direction. And when it is going in the radial direction, now that flow is tilted by certain angle. And this is called as pre-whirl. This is called as pre-whirl. Why are we calling it as pre-whirl? Because if you see this velocity v1, this will introduce a component that is called as vw1. Earlier the vw1 was 0, but now it will introduce a component that is component of v1 in the direction of u1. This will be your vw1. So this is what is the pre-whirl, or whirl is there. When the fluid is entering the blade, it is having a whirl velocity vw1. Understanding? So this is your guide vane. This is your guide blade or guide vane. Okay. Where is this installed? This guide vane is installed at the inlet of the compressor. So you see that this is how your compressor would actually look like. Okay. Generally the compressor blades are present. Somewhere. Generally the compressor blades are present somewhere over here. The blades are present over here where the actual compression takes place. So the flow that is coming axial is tilted in the radial direction over here by the impeller. So now where do you install the blades? So the guide blades are actually installed at this location. So if you see over here, this is how your blades will be looking. Okay. So if you see your actual impeller casing, the impeller casing will be something like this. So this is how the outer casing will be looking like. Okay. So this is how your outer casing will be looking like, and there will be guide blades present over here. Okay. So this is your guide blade. Okay. So the flow which is coming inside like this, that will be tilted by these guide blades. So these guide blades will be tilting it in the vertical direction as well, and then it will be tilting in the pre-whirl direction as well. So that when the flow is actually entering inside the compressor, so I will draw it, let's say, by this color. Is it clear? The blue one. Okay. So now you see that your flow which is going radially, it was supposed to enter the blade radially, but now it has been tilted by certain angle, and this theta is called as pre-whirl angle. Okay. This is pre-whirl angle. Understood? Okay. So now in the question he says the air is given a pre-whirl of 15 degrees. Okay. So now how do we solve this question? So this was a very good question. This was one of the best questions that you can think of in case of a centrifugal air compressor. So he says that it runs at 20,000 RPM, air enters at 300 Kelvin, and 1 bar diameter of the inlet of the compressor is 10 centimeter. So you see that he has given you diameter of inlet of the compressor. So when he is giving you diameter of the inlet, this is your DI. Can you tell me whether he has given you what is the axial velocity? What is the axial velocity at entry? How do we say? So let's say we assume that, let's assume that mass flow rate of air is 1 kg per second. Mass flow rate of air that is going inside is 1 kg per second. If this is the mass flow rate, then can we calculate what is the volume of air that is going inside? So volume of air will be equal to mRT divided by P. So mass flow rate is 1 multiplied by 287 multiplied by 300 divided by 10 raised to power 5. So this will be your volume of air that will be sucked inside the compressor per second. Okay. So this will come out to be 287 multiplied by 300. Okay. Divided by 10 raised to power 5. Okay. So divided by 10 raised to power 5 will be 0.861. So 0.861 meter cube per second. This is the volume flow rate of air, volume that is going inside. Now this volume flow rate of air will be equal to, it will be equal to area at the inlet multiplied by velocity axial, because the flow is axial at the inlet. Okay, the flow is axial at the inlet. Okay, so if this is axial at the inlet, we can calculate what is the axial velocity with which it is coming. So from here, you can calculate velocity of axial will be equal to 0.861 divided by pi d inlet square divided by 4. Okay, so we will calculate this. So equal to divided by pi d square by 4 divided by pi multiplied by 4 divided by 0.1 square. So this is coming out to be 109.62. So 109.62 meter per second. So you see that this is the axial velocity with which your flow is coming inside. Now you see that if this is the axial velocity with which it is coming, can I say this velocity will also be equal to V1? Can I say this will also be equal to V1? So you see that the air that is coming inside is coming with V axial. Now that is converted in the radial and that is tilted. So it will be V1. Okay. So you have calculated V1 velocity. If you have calculated V1, so now you see that you have calculated V1. Now you can calculate VW1 as well. Okay. So once we have calculated V1, now we need to calculate power. So power can be written as m dot VW2 U2 minus VW1 U1. Is it clear? Okay. So VW2 U2 minus VW1 U1. So now we will calculate what are velocity U2, what are velocity U1, and then we will proceed. So you see that he has given you that the inlet to the compressor is 10 centimeter and exit of the blade is 20 centimeter. Also, there is a pre-whirl of 15 degrees and it is running at 20,000 RPM. So now we will calculate what is U2 and VW2. Okay, so from here you can calculate power that is required is m dot A, that is 1 multiplied by VW2. So let's calculate VW2. So we know that VW2 will be equal to U2, that is equal to pi d2n divided by 60. Okay, since he has not given you anything about whether the impeller or whether the compressor is radial or it is backward curved or forward curved, so we will assume that the compressor is always radial. Okay, so velocity U2 will be equal to pi multiplied by d2 is 0.2 multiplied by RPM is 15,000. Oh, sorry, 20,000. So pi dn, pi 20,000 divided by 60. So U2 is 209.43. Okay, meter per second. Okay, and what will be U1? U1 will be less than this, that is half of this. So pi into d1n divided by 60. Okay, so you see that it will come out to be half of that because the diameter is 0.1. Okay, so 104.71. So now you see that, guys, there is a small catch over here. You see that he has not actually given you what is the diameter of the blade at inlet. He has not given you what is the diameter at the inlet of the blade. So generally we assume that your blade starts from the inlet diameter. Okay, mostly your blade that you see in a compressor, that will actually start from, generally the blade not start from here. Most of the blades are starting from the inlet location only. Okay, so most of the time we assume that your blade that is starting from the inlet diameter to the exit diameter. Whatever is the diameter of the eye, at that location only your blade generally starts. Is it clear? So we will take U1 as pi d1 into n divided by 60, and once you have calculated this, now you can calculate what is the power required. So 209.43 square minus 104.79 multiplied by VW1. What is VW1? VW1 will be equal to V1 cos 15 degree. Okay, so from here you can calculate VW1, that is V1, sorry, not cos of 15 degree, sine of 15 degree. Okay, V1 sine of 15 degree. Why sine? Because this angle is pre-whirl, that is 15 degree. So VW1 will be component of this. So this is 75 degree. So V1 cos 75 or V1 sine 15. Okay, V1 is 109. So V1 is 109.62. 109.62 multiplied by sine of 15. Okay, so sine of 15, this comes out to be 28.37. Okay, so we take this value 28.37 and we put it over here. Is it clear? Okay, so this will be your amount of work done. So multiplied by 104.79, so minus 209.43 whole square. So this is 40.887. So power will come out to be 40.887 kilojoule per kg. Okay, so this is the amount of energy required. For compressing 1 kg of air. Is it clear? So 40.887. This was an excellent question. Is it clear? Understood? So I hope everybody might have understood the concept of pre-whirl now. Why we actually employ the pre-whirl? We employ the pre-whirl to remove the shock wave formation at the inlet. Why the shock waves are formed? Shock waves are formed because of very high inlet velocity of the air compressors. Generally, compressor runs at more than 25,000 RPM. So because of that, your U1 becomes very high. Also, your V1, the velocity with which your fluid is entering, you see that V1 coming over here is 109 meter per second. So V1 is very high, extremely high. V1 is high, U1 is high. The relative velocity, which is a combination of both of these, will again become higher. So that might cross the supersonic or the sonic velocity. Is it clear to everyone? Is it clear? Okay. So if it is clear, now let's go ahead to the next question. Okay. So it says a centrifugal air compressor runs at 12,000 RPM. Air enters at 300 Kelvin and 1 bar. Diameter at the inlet of blade is 10 centimeter and the exit is 30 centimeter. The blade angle at exit is 70 degrees. So you see that now the blades are not radial. That means beta is not 90 degree, now beta is 70 degree. If the velocity of flow is constant at 50 meter per second, then the work required per kg of air to run the compressor is. So to calculate this, we know that the blades are not radial at exit, but generally the blades will be radial at inlet. So VW1, this is your 0. This we know that for unless the pre-whirl is given, VW1 will always be 0. Okay. So now we will draw the exit velocity triangle. So if you draw the exit velocity triangle, so this is how your blade is looking like this. Okay. And when you draw the velocity triangle, this is your VR2. Okay. So this is how your triangle will be looking like. Okay. So this is your VR2. It will be in this direction. Okay. And you have U2 and this will be your VW2. Okay. So he has given you that this is your 50 meter per second VF. He has given you 50 meter per second. Okay. So this is how the question is given. So now how do we calculate VW2? VW2 is nothing but VW2 can be written as VW2 is equal to U2 minus VR2 cos of 70 degree. Okay, so V2 minus VR2 cos of 70 degree. This can be written. Okay, or it can also be written that, see, if you see over here, velocity of flow is constant. So 50 meter is given. This velocity of flow is given 50 meter. So you see that this 50 and this, let's say I write A, B, C, D. Okay. So I can write VW2 is U2 minus AB. I can write this quantity as V2 minus AB. And how do we calculate AB? So you see that 50 divided by AB will be 1070 degree. So 50 divided by AB, this will be your 1070 degree. So from here you can calculate AB. Okay. So AB will come out to be 50 divided by 10 of 70 degree. So that is equal to 50 divided by 10 of 70. So 10 of 70 will be very high. So 18.19 meter per second. So you see that AB is calculated. Now once AB is calculated, you can calculate VW2. To calculate VW2, you will require U2. And how do we calculate U2? U2, the diameter is given at outlet and the RPM is given. Okay, so you can calculate U2 is equal to pi d2n divided by 60. Okay, so a compressor runs at 12,000 RPM and diameter at exit is 30 centimeter. Okay, so pi multiplied by 0.3 multiplied by 12,000 divided by 60. This is your U2. Okay, so how much it is coming? So pi multiplied by 0.3 multiplied by 12,000 divided by 60. So 188.49. Okay, so 188.49 meter per second. Once you have calculated this, now you can calculate VW2. Okay, so VW2 will be equal to minus of 18.19. So 170.30. 170.30 meter per second. This will be your VW2. Understood? Is it clear to everyone? Okay. So now if this is your VW2, you can calculate what is the power required per kg of mass flow. So power required per kg of mass flow will be equal to VW2 U2. Okay. And this will be equal to 170.30 multiplied by 188.30 or 188.49. Okay, 188.49. Is it clear? Multiplied by 188.49, so that comes out to be 32.100. So 32.100 kilojoule per kg. Is it clear? Power required per kg of mass flow is 32.100. I hope everybody might have got it. Yes or no? Okay, so this was again a very easy question. So 32.1. Is it clear? Okay, very good. So if this is clear, then let's go to the next question. Again, guys, last two questions were very easy. Okay, so it says a centrifugal compressor runs at a speed of 15,000 RPM and it delivers 30 kg of air per second. The work done on the compressor is 28.8 kilojoule per kg of air. Then the torque on the compressor is. So we know that torque will be equal to, or we can write torque multiplied by omega, that is equal to the power. Okay, so he is asking you torque. So torque can be written as torque is equal to power divided by omega. And what is the power that is supplied by the compressor? So you see that the compressor is doing 28.8 kilojoule per kg of work, and there is a air supplied that is 30 kg per second. So what will be the power? Power will be equal to 28.8 multiplied by 30. This is the work done, but this work done is per minute. Okay, so divided by 60. So this is the work done per second. Work done per second. So this is work done per second divided by omega. So omega is equal to 2 pi n divided by 60. Okay, so you can write it like this. So 60 will cancel. So this will come out to be 28.8 multiplied by 30 divided by 2 multiplied by pi multiplied by n is your 15,000. Okay, is it clear? So we will calculate this. You will see that this value will come out to be very small. So 28.8 multiplied by 30 divided by 2 divided by 15,000 divided by pi. Okay, so this comes out to be I am sorry, 30 kg of air per second is given, not per minute. I am sorry. So this will be equal to This is equal to 28.8 multiplied by 30 divided by 2 pi and divided by 60. Okay. So 28.8 multiplied by 30 multiplied by 60 divided by 2 pi multiplied by 15,000. Okay. So the value will come out to be multiplied by 60, that is 0.55. Is it coming out to be 0.55? 0.55, or it is coming out to be 5.5? Let me check the answer once again. So 28.8 kilojoule per kg. Okay, so we have this value is 28.8 kilojoule. So you have to multiply it with 1000 as well. Okay, so 1000. Why 1000? Because the power that you are supplying is in joule. Okay, so we will calculate everything in SI unit. Okay, so multiplied by 1000. 28.8 multiplied by 30 multiplied by 1000 divided by 2 pi n multiplied by 60. Okay, so this value will come out to be 550. Okay, so 550 are 0.55, 550 Newton meter. Okay, he is asking you kilonewton meter. Just let me check it once again, the calculation. It looks like I am making some mistake. 28.8 multiplied by 30 kg multiplied by 1000 divided by 2 divided by pi divided by 15,000 multiplied by 60. So 550. Okay, so 550 Newton meter. 550 Newton meter is 0.55 kilonewton meter. Is it clear? So the answer will be 0.55 kilonewton meter. Understood? Okay. Okay, very good. Let's go to the next question. This is the last question. So it says a centrifugal air compressor handles 540 kg per minute of air at a speed of 20,000 rpm. The air enters the impeller eye with no pre-whirl. The ratio of whirl speed to tip speed is 0.9. So he is saying VW2 divided by U2 is 0.9. So basically he has given you PS. Okay, so this is your PS. Okay, the diameter of tip is 426 mm. Then the power required is. So now you see that what is he is calculating the power required. So to calculate power required, you need to calculate U2. U2 can be written as pi d2n divided by 60. Okay, so this is pi multiplied by 0.426 multiplied by n. N is your, it runs at 20,000 rpm. So 20,000 divided by 60. Okay, pi dn divided by 60. Okay, so you see this value will come out to be pi multiplied by 0.426 multiplied by 20,000 divided by 60. So this comes out to be 446. 446.10 meter per second. This is your U2. Okay, so if this is your U2, you can calculate what is the power. So power required per kg will be equal to, power required or the total power will be equal to m dot A multiplied by VW2 U2. Okay, so that will be equal to m dot A. M dot A given is the mass flow rate is 540 kg per minute. Okay, so 540 divided by 60 multiplied by 0.9 multiplied by, so VW2 is 0.9 times of U2. Okay, so this will become U2 square. So 446.10 whole square. Okay, so this will come out to be 446.10 square multiplied by 0.9. Okay, multiplied by 540 divided by 60. So this comes out to be 1611. 1611.98 kilowatt. Is it clear? Is it clear? Okay, so 1611.98. Okay, it is asking round off to nearest integer. Okay, so in kilowatt, you can write 1611.98 kilowatt. Nearest integer will be 1612. Is it clear to everyone? Okay, so if it is clear, guys, we have come to end of our DPP. I hope most of you guys might have solved the questions you might have tried. Okay, and these are some of the best questions you can think of. These questions were not easy. Some of the questions were slightly difficult, but I am sure you might have solved it. Okay, so that's all. Thank you so much.